So the generalization to several inequality constraints and several variables is not too bad, and the main thing that we need to consider is whether any of the inequality constraints are binding or not binding, right? So the generalization is straightforward. But we must consider all permutations of binding and non-binding constraints. So let's just walk through the theorem and see exactly what it says. Well, suppose, of course, that f, g1, all the way up to gk are C1 functions of n variables. Suppose that x star in my domain, Rn, is a local maximizer of f on the constraint set given by g1 of x is less than or equal to b1 all the way up to gk of x is less than or equal to bk. Well, if the constraints gi1, gi2 up to ga are the binding constraints, that is gi1 of x star is actually equal to bi1, and that holds for all the indices up to ia. Right, so these I1, I2, IA are just sub-indices from this set. So I'm just picking an arbitrary collection of things to bind. Further suppose so this is the generalization of the NDCQ for the inequality case. So we've got to have that the Jacobian of gi1, these functions gia, with respect to the variables, all the variables in play, x1 up to xn. And of course, this guy looks like dg I sub 1 dx, and I evaluated x star, dg I1 dxn, this should be 1, x star, all those rows down to dg ia dx1 of x star, all the way over to dg ia dxn x star has rank A, which is equal to the number of rows, and this is the NDCQ, this guy right here. That's the thing that we always have to check before we move on. So now form the Lagrangian. And it looks like it always does. L of x1 up to xn. I have lambda, and now I have a lambda for every single constraint. And this is defined to be my f of x minus lambda 1 g1 of x minus b1 minus dot 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 all the way up to the kth constraint so you form that function. Well, then there exists, now we discuss the first order conditions. There exist multipliers lambda 1 star, lambda 2 star, all the way up to lambda k star, such that A, we're going to have that the first partials with respect to the x variables are all going to vanish. So all the way up to dxn of the Lagrangian. Those all vanish. The second thing is that I've got a complementary slackness condition for every single index here. So lambda 1 star. So for every single constraint function, I have a complementary slackness condition. Right, so this is the complementary slackness condition for the first constraint all the way up to the last constraint. GK x star minus BK is equal to 0. C, all of my multipliers have to be greater than or equal to 0. And finally, D, of course I have to satisfy the constraints. And these are the conditions that you'll write down in general. Next, we're going to work an example where we do multiple constraints and we see exactly how we perform all these manipulations.